SEC calibration theory. Introduction. Welcome back to the Chromperfect chromatography theory series. In the previous video, we examined SEC integration theory. We considered the dedicated SEC baseline, the treatment of detector noise, the use of an internal standard to correct between-run flow variation, the different types of detector response, and the calculations used to describe a molecular weight distribution. In this video, we will move from integration to calibration. An SEC chromatogram initially provides detector response as a function of elution time or elution volume. To produce molecular weight information, we require a calibration relationship that connects each position in the chromatogram with a molecular weight, molecular size, or hydrodynamic volume. We will begin by reviewing the meaning of molecular weight averages. We will then examine the general properties of an SEC calibration curve, the use of narrow molecular weight standards, universal calibration, the importance of viscosity, and the use of broad molecular weight distribution standards. This discussion assumes familiarity with the basic principles of size exclusion chromatography and with general calibration concepts such as data points, curve fitting, and polynomial calibration models. Molecular weight averages. Size exclusion chromatography separates analyte molecules according to their effective size in solution. Although SEC can occasionally be useful for molecules with molecular weights below approximately 1,000, its principal application is the separation and characterization of macromolecules. The boundary between an ordinary molecule and a macromolecule is not exact. A molecule may be considered a macromolecule when it is sufficiently large to display properties that begin to resemble those of macroscopic material. Under suitable conditions, for example, macromolecules can scatter enough light to become visible using specialized optical techniques. The historical development of macromolecular chemistry came from several scientific directions. Organic and physical chemists studied synthetic polymers whose chemical structures were generally known. Biochemists studied naturally occurring polymers, including proteins, nucleic acids, carbohydrates, and polyisoprenes, whose structures were often considerably more complex. When every molecule within a polymer sample is identical, the polymer is described as monodisperse. Pure proteins and nucleic acids may be considered examples of monodisperse polymers because their molecules normally have defined compositions and molecular weights. Many natural polymers and almost all synthetic polymers are polydisperse. During polymerization, the growing polymer chains do not all terminate at the same length. Termination occurs at different stages of growth, producing a mixture of molecules containing different numbers of monomer units, and therefore a range of molecular weights. A polydisperse polymer does not have one uniquely defined molecular weight. Instead, its distribution can be described using several molecular weight averages. 4 averages are especially common: the number average molecular weight, Mn, the weight average molecular weight, Mw, the Z average molecular weight, Mz, and the viscosity average molecular weight, Mv. Chromperfect can also calculate the higher order Z+1 average, Mz+1. For a truly monodisperse material, all molecular weight averages are equal to the ordinary molecular weight of the molecules. For a polydisperse material, the averages differ because each one gives a different statistical weighting to the molecules within the distribution. The number average molecular weight gives each molecule equal importance. Imagine a sample containing many molecules with different molecular weights. To calculate the number average, the molecular weights of all molecules are added together and divided by the total number of molecules. A small molecule therefore counts exactly as much as a large molecule in determining the average. The number average is obtained experimentally by methods that depend upon colligative properties. Colligative properties depend primarily upon the number of dissolved particles rather than their individual sizes. Osmotic pressure measurements are one example. The weight average molecular weight gives greater importance to the larger molecules because each molecule is weighted according to its mass. A molecule with twice the molecular weight contributes twice as strongly as a smaller molecule. Large-angle light-scattering measurements commonly provide the weight average molecular weight. The Z-average applies an even stronger weighting to the high molecular weight region. Small-angle light scattering and sedimentation measurements may provide information associated with the Z-average. The viscosity average molecular weight is derived from the effect of the polymer on solution viscosity. Its position relative to the other averages depends upon the Houwink exponent, alpha. For the usual positive values of alpha, the viscosity average normally lies between the number and weight averages. Each molecular weight average is associated with different physical properties. Mn is influenced strongly by the number of polymer molecules and is therefore related to properties that depend upon the number of chain ends. Mw gives greater significance to larger chains and is often more closely related to bulk mechanical properties. Mz and higher averages are particularly sensitive to the high molecular weight tail of the distribution. Mv describes the molecular weight that corresponds to the observed viscosity behavior under the applicable polymer, solvent, and temperature conditions. For a normal polydisperse distribution, the averages generally occur in the following order. Mn is less than or equal to Mv. Mv is less than or equal to Mw. Mw is less than or equal to Mz. Mz is less than or equal to Mz plus 1. The precise relationship involving Mv depends upon alpha, but the important principle is that progressively higher order averages place progressively greater emphasis upon the largest molecules. This difference between the averages is not a mathematical inconvenience. It provides information about the breadth and shape of the molecular weight distribution. One of the most common measures of distribution breadth is the ratio of Mw to Mn. This ratio is often called the polydispersity index, or dispersity. For a monodisperse polymer, Mw and Mn are equal, and the ratio is 1. As the distribution becomes broader, Mw moves farther above Mn, and the ratio becomes larger. A distribution can never have an Mw divided by Mn value below 1 when both averages are calculated correctly from the same non-negative distribution. A broad distribution is not necessarily undesirable. The required molecular weight profile depends upon the intended material and its application. However, the relationship among the averages provides a compact way to describe the distribution and to compare materials or manufacturing batches. General properties of an SEC calibration curve. An SEC calibration curve establishes the relationship between chromatographic position and molecular weight. The chromatographic position may be expressed as elution time or elution volume. Strictly speaking, SEC separates according to elution volume. Elution time is commonly used because when flow rate is stable, time is directly proportional to volume. The molecular weight axis is normally logarithmic. This is necessary because an SEC separation may cover several decades of molecular weight. A useful column may separate material ranging, for example, from molecular weights of 1,000 to 1 million. Representing molecular weight on a linear axis would compress much of the useful range. Plotting the logarithm of molecular weight provides a more practical relationship. For conventional SEC, large molecules elute first. Large molecules are excluded from a greater proportion of the pores within the stationary phase. They therefore follow a shorter effective path through the column. Smaller molecules can enter more of the pore volume and take longer to pass through the column. Consequently, an ordinary SEC calibration curve slopes downward. Early elution corresponds to high molecular weight, while later elution corresponds to low molecular weight. Every SEC column has an upper and lower separation limit. At the upper limit, molecules are too large to enter any significant fraction of the pores. These molecules are fully excluded and elute together near the column's exclusion volume. Beyond this point, the column cannot distinguish one very large molecule from another. At the lower limit, molecules are small enough to enter essentially all accessible pores. These molecules are fully included and elute near the total permeation volume. Below this point, the column again loses its ability to discriminate according to size. The useful calibration range lies between the fully excluded and fully included regions. Within that range, elution position changes with molecular size. The calibration relationship is often approximately linear when logarithmic molecular weight is plotted against elution time or volume. However, it is not necessarily perfectly linear across the complete working range. The relationship may curve near the limits of the column, or when the packing contains a complex pore size distribution. Chromperfect therefore supports polynomial calibration curves rather than requiring every set calibration to be linear. The degree of the selected polynomial must be justified by the available calibration data. A higher degree curve can follow curvature more closely, but it also requires more reliable and well-distributed data points. Using a polynomial degree that is too high for the number or quality of the calibration points can create unrealistic bends between points. These bends may not be obvious when looking only at residual statistics, but they can produce serious errors when sample data are converted to molecular weight. The curve should therefore be no more complex than the data require. The calibration standards should cover the molecular weight range expected in the samples. Extrapolation beyond the standard range is particularly hazardous in SEC because the calibration is logarithmic. A small extension in elution time may correspond to a large change in calculated molecular weight. Polynomial curves can also behave unpredictably outside the region constrained by their calibration points. Results outside the calibrated range should therefore be treated with caution, even when the software can calculate them. Narrow standard calibration. The most direct SEC calibration method uses a series of standards with narrow molecular weight distributions. Ideally, each standard is monodisperse or sufficiently narrow that all its molecular weight averages can be treated as equal within the precision of the physical measurements. In practice, even a truly monodisperse standard produces a chromatographic peak with finite width. Part of this width results from injection and extra column effects, while part is produced by diffusion and other broadening processes within the column. For narrow standard calibration, the elution position of the peak top is associated with the nominal molecular weight of the standard. Each standard therefore contributes a calibration data point. The elution time or volume determines the horizontal position, and the logarithm of the nominal molecular weight determines the vertical position. A series of standards spanning the working range produces a set of points from which the set calibration curve is fitted. The calibration produced directly from narrow standards of the same polymer type as the samples is commonly described as the true calibration curve. The word true should be understood within the assumptions of SEC. The value of the curve at a given elution volume represents the molecular weight assigned to material of that polymer that elutes at that volume. Narrow standard calibration is normally preferred when suitable standards are available. It is direct, conceptually straightforward, and does not require the analyst to reconstruct the calibration from a broad distribution. However, suitable narrow standards may not exist for the polymer being analyzed. Even when standards are available, they may not cover the required range, or may not remain stable under the chosen solvent and temperature conditions. It is also common for a laboratory to have good narrow standards for one polymer, such as polystyrene, but need to analyze a chemically different polymer. This creates the need for universal calibration. Universal calibration curves. Universal calibration begins with an important limitation of ordinary molecular weight calibration. Different polymers can produce different molecular weight calibration curves on the same column, even when the solvent, temperature, flow rate, and all other chromatographic conditions remain unchanged. Two polymers may produce parallel calibration curves separated by a constant vertical distance. In that case, using the calibration for one polymer to analyze the other produces molecular weights that are wrong by a constant factor. Other pairs of polymers produce calibration curves with different slopes. In that situation, the error is not constant. The calculated molecular weight error changes across the distribution. This occurs because SEC does not directly separate molecules according to molecular weight. It separates them according to their effective size in solution. Molecular weight and molecular size are related, but the relationship depends upon chemical structure, chain flexibility, branching, solvent interactions, temperature, and polymer conformation. Two polymers with the same molecular weight may occupy different effective volumes in solution and therefore elute at different times. If the relationship between molecular weight and molecular size is known for both the calibration polymer and the sample polymer, a column can be calibrated using one polymer and the results converted for another. The objective of universal calibration is to construct a calibration relationship based on molecular size rather than on the molecular weight of one particular polymer. The Q-factor method, an early universal calibration approach, assumed that molecular size for SEC purposes was proportional to the fully extended molecular length of the polymer. A proportionality constant, called the Q-factor, was used. The Q-factor is the molecular weight divided by the fully extended molecular length. Because different polymers contain monomer units of different masses and structures, their Q-factors differ. For example, a styrene monomer has a molecular weight of approximately 104. If each monomer contributes approximately 2.5 angstroms to the fully extended chain length, the Q-factor for polystyrene is approximately 41 Daltons per angstrom. A vinyl chloride monomer has a molecular weight of approximately 65 and contributes a similar length. Its Q-factor is therefore approximately 25 Daltons per angstrom. For equal fully extended molecular lengths, polyvinyl chloride has a lower molecular weight than polystyrene. If molecules with equal length elute at equal positions, the calibration curve for polyvinyl chloride should lie below that for polystyrene. To create a calibration based on molecular length, the molecular weight of each standard is divided by the Q-factor for the standard polymer. The logarithm of this adjusted value is plotted against elution time or volume. When a different polymer is analyzed, the length-related value is read from the curve and converted back to molecular weight using the Q-factor for the sample polymer. The attraction of this method is that the Q-factor can be estimated from the known chemical structure without requiring additional laboratory measurements. However, fully extended chain length is not always a reliable representation of the size that determines SEC separation. Polymer chains in solution normally exist as coiled structures rather than fully extended rods. Different polymers can form coils with different shapes and degrees of expansion. The Q-factor method works reasonably only when the molecular weight calibration curves for the standard and sample polymers are parallel. That condition is frequently not satisfied and may be impossible to verify when suitable sample polymer standards do not exist. The Q-factor approach is therefore limited and is now rarely used, although Chromperfect supports it. A more successful universal calibration approach uses hydrodynamic volume, a concept closely associated with solution viscosity. Introduction to viscosity. Before SEC became widely available, this was one of the principal techniques used to estimate polymer molecular weight. SEC has replaced many traditional vicometric methods in routine analytical work, but viscosity remains central to polymer characterization and SEC calibration. Independent viscosity measurements are often used to characterize calibration standards. They also provide the theoretical basis for relating the molecular sizes of chemically different polymers. Viscosity describes a fluid's resistance to flow. A liquid such as water has relatively low viscosity, while a liquid such as heavy oil has much higher viscosity. When a polymer is dissolved in a solvent, the polymer molecules generally increase the viscosity of the solution. The magnitude of that increase depends upon the amount of polymer and the hydrodynamic volume occupied by the polymer molecules. A polymer molecule moving through a solvent interacts with and effectively carries part of the surrounding solvent. The molecule and its associated solvent behave as a hydrodynamic unit. The effective volume of that unit is the hydrodynamic volume. Hydrodynamic volume depends upon molecular weight, but also upon molecular structure, conformation, branching, solvent, and temperature. A flexible polymer chain in a good solvent may form an expanded coil with a relatively large hydrodynamic volume. The same polymer in a poorer solvent may form a more compact coil. Two chemically different polymers of equal molecular weight may therefore have different hydrodynamic volumes. SEC separation responds more closely to hydrodynamic volume than to molecular weight alone. This makes hydrodynamic volume a more useful basis for universal calibration. Several viscosity terms are used when characterizing polymer solutions. The relative viscosity is the viscosity of the polymer solution divided by the viscosity of the pure solvent. The specific viscosity is the relative viscosity minus 1. It represents the fractional increase in viscosity caused by the dissolved polymer. The reduced viscosity is the specific viscosity divided by polymer concentration. The inherent viscosity is the natural logarithm of the relative viscosity divided by concentration. Both reduced and inherent viscosity depend upon concentration. Intrinsic viscosity is obtained by extrapolating the appropriate viscosity relationship to zero polymer concentration. It is represented by the symbol eta in square brackets. Because it refers to the limiting behavior at infinite dilution, intrinsic viscosity is a characteristic property of the polymer, solvent, and temperature combination. Intrinsic viscosity is related to the effective volume occupied by polymer molecules in solution. The product of intrinsic viscosity and molecular weight is proportional to hydrodynamic volume. This relationship provides the foundation for modern universal SEC calibration. The relationship between intrinsic viscosity and molecular weight is commonly described by the Houwink equation. Intrinsic viscosity equals kappa multiplied by molecular weight raised to the power alpha. Kappa and alpha are empirical constants. Their values depend upon the polymer, solvent, and temperature. The same polymer can therefore have different Houwink constants under different experimental conditions. Alpha describes how rapidly intrinsic viscosity increases with molecular weight. It is related to polymer conformation and the quality of the solvent. Kappa establishes the scale of the relationship using this with SEC calibration curves. The product of intrinsic viscosity and molecular weight is used as a measure of hydrodynamic volume. Substituting the Houwink relationship gives hydrodynamic volume proportional to kappa multiplied by molecular weight raised to the power alpha plus 1. This provides a way to transform a molecular weight calibration for one polymer into a hydrodynamic volume calibration. When calibrating with narrow standards, the molecular weight of each standard is known. If the Houwink constants for the standard polymer are also known, its intrinsic viscosity and hydrodynamic volume can be calculated. The calibration points can then be expressed as hydrodynamic volume rather than standard molecular weight. The resulting curve should, within the assumptions of universal calibration, apply to other polymer types. When a sample polymer is analyzed, the hydrodynamic volume corresponding to each elution position is read from the universal curve. The Houwink constants for the sample polymer are then used to convert hydrodynamic volume back into sample molecular weight. Universal calibration, therefore, requires information for both materials. The standard polymer constants transform the original standards into hydrodynamic volume. The sample polymer constants transform hydrodynamic volume into the molecular weights of the material being analyzed. When Houwink constants are not available for the standard polymer, intrinsic viscosities can instead be measured directly for the narrow standards. Each standard's known molecular weight is multiplied by its measured intrinsic viscosity to obtain the hydrodynamic volume calibration value. Houwink constants for the sample polymer are still required if the final result is to be expressed as sample molecular weight. Universal calibration is powerful, but it depends upon the validity of its assumptions. Molecules with equal hydrodynamic volumes are assumed to elute at the same position. The Houwink relationships must be valid over the molecular weight range of interest. The constants must correspond to the actual polymer, solvent, and temperature. Interactions between the polymer and stationary phase must be absent or negligible. SEC should operate by size exclusion rather than adsorption, ionic interaction, or another separation mechanism. Universal calibration cannot correct a fundamentally non-size exclusion separation. Using broad standards for SEC calibration. Narrow molecular weight standards are not always available for the polymer of interest. Universal calibration may also be impractical because the necessary Houwink constants or viscosity information are unavailable, uncertain, or inappropriate for the system. Under those conditions, the column may be calibrated using one or more broad molecular weight distribution standards. Frequently, only one broad standard is available. A broad standard cannot be represented by one peak-top molecular weight. Its chromatographic profile contains a range of molecular weights. To be useful for calibration, the distribution must therefore be independently characterized. Chromperfect supports three related approaches: the integral method, the Hamilec method, and the Yau method. The integral method. The first broad standard method is called the integral method because it uses the integrated elution profile. This method requires a molecular weight distribution table for the standard polymer. The table relates cumulative distribution percentage to molecular weight. For example, it may state that 10% of the polymer mass lies above a molecular weight of 500,000, 20% lies above 250,000, and so forth. To produce such a table experimentally, the broad polymer can be divided into fractions, and the molecular weight of each fraction determined independently. Creating a reliable molecular weight distribution table is therefore not a simple task. Fortunately, commercially supplied broad standards may include a characterized distribution table. To calibrate a column using the integral method, the broad standard is analyzed under the conditions to be calibrated. The detector response is integrated across its elution profile. Chromperfect determines the elution position associated with each cumulative percentage listed in the standard's distribution table. Each cumulative percentage provides a connection between a molecular weight in the table and a time or volume in the chromatogram. Those paired values become the calibration data points. Suppose the standard documentation states that 10% of the mass lies above a particular molecular weight. Beginning at the high molecular weight, early elution side of the chromatogram, Chromperfect determines the point by which 10% of the total integrated response has eluted. That elution position is associated with the stated molecular weight. The process is repeated for the remaining entries in the distribution table. A single broad standard can therefore provide several calibration points rather than only one. The quality of the calibration depends upon the quality and spacing of the cumulative distribution data. A table with several well-distributed entries provides more information than one containing only a few closely spaced points. The detector response must also correspond to the distribution basis used in the table. For example, a mass distribution table should be used with a detector whose response can be interpreted appropriately as mass response. The broad standard must be analyzed within the detector's linear range, and the baseline and processing limits must be reliable because errors in cumulative area affect the derived calibration positions. Multiple broad standards or replicate analyses may be used. Each standard or replicate can be represented as a calibration level. The several sets of derived points are then combined when fitting the final calibration curve. The integral method and universal calibration. The integral method can also be combined with universal calibration. When the broad standard's distribution is expressed in molecular weight, Mark, Houwink, or viscosity information can be used to convert the standard molecular weights into hydrodynamic volumes. The resulting calibration can then be converted for a chemically different sample polymer. As with narrow standard universal calibration, this requires valid information for both the standard and the sample polymer. The Hamilec Method. Some broad standards are supplied without a complete molecular weight distribution table. Instead, they may be characterized only by two molecular weight averages, normally Mn and Mw. These values can still be used to estimate a calibration through the Hamilec method. The Hamilec method is named after the principal investigator in the laboratory where it was developed. It is also called the linear method because a single broad standard produces a linear calibration curve. The method begins with a tentative linear relationship between logarithmic molecular weight and elution time or volume. The chromatographic profile of the broad standard is processed using that tentative curve. From the assigned molecular weight at each point and the detector response distribution, calculated values of Mn and Mw are obtained. The calibration curve is then adjusted iteratively. After each adjustment, Mn and Mw are recalculated. The process continues until the calculated averages agree with the independently assigned Mn and Mw values for the standard. Once agreement is achieved, the positions on the adjusted calibration curve corresponding to Mn and Mw are used to create a pair of calibration data points. With only one broad standard, the result is necessarily a linear calibration because only two independent points are obtained. If several broad standards are used, each produces a pair of points. The combined data may then support a nonlinear calibration curve. Replicate analyses can also provide repeated pairs of points, improving the statistical basis without increasing the number of distinct molecular weights represented. The Hamilec method is attractive because it requires only two independently measured molecular weight averages rather than a complete distribution table. However, it is affected by column broadening. Every SEC peak is broader than the distribution that would be observed in a perfect separation without diffusion, injection, spreading, or extra column effects. For a broad standard, this additional broadening increases the apparent separation between the low and high molecular weight portions of the chromatogram. The Mn and Mw positions derived from the broadened profile are therefore farther apart than they would be without column broadening. The resulting Hamilec calibration curve tends to rotate counterclockwise relative to the true calibration curve that would be obtained from narrow standards. The curve is therefore not a direct estimate of the true molecular weight versus elution relationship. However, its distortion can partially compensate for the same broadening when samples are subsequently analyzed. This compensation is reliable only when the sample has approximately the same molecular weight distribution shape and breadth as the broad standard. If the sample distribution differs substantially from that of the standard, the correction no longer matches the sample, and molecular weight results may be inaccurate. This restriction limits the general usefulness of the uncorrected Hamilec method. The Yau method. Yau and colleagues developed a modification of the Hamilec approach that attempts to correct the calibration for column broadening. The method assumes that the contribution of column broadening is independent of elution time and can be represented by a single value called the column sigma. Column sigma is the standard deviation, expressed in time or volume units, of the peak that would be produced by a monodisperse sample because of the column and associated system broadening. The observed broad standard profile contains both the genuine molecular weight distribution of the standard and the additional spreading introduced by the chromatographic system. Using the column sigma estimate, the Yau method corrects the calibration relationship to remove the counterclockwise rotation associated with the ordinary Hamilec result. The corrected curve should lie closer to the true calibration curve that would have been obtained using narrow standards. Because the calibration is corrected toward the underlying column relationship, it should be more applicable to samples whose molecular weight distributions differ from that of the broad standard. The usefulness of the Yau correction depends upon the validity of the column sigma assumption. Actual broadening may vary with elution position, molecular size, flow rate, column condition, and other factors. Reducing the complete broadening process to one constant is an approximation. The column sigma value must also be estimated accurately. An incorrect value can undercorrect or overcorrect the calibration. The Yau method should therefore be understood as a model-based improvement rather than a complete elimination of chromatographic broadening. Relationship between the three broad standard methods. The integral, Hamilec, and Yau methods use different information about the broad standard. The integral method uses a molecular weight distribution table containing several cumulative percentages and corresponding molecular weights. It can produce several calibration points from one standard. The Hamilec method uses only Mn and Mw. It iteratively adjusts a calibration until the calculated averages match those assigned to the standard. A single standard produces 2 points, and therefore a linear curve. The Yau method begins from the same type of Mn and Mw information, but adds a correction based upon the estimated column sigma. The integral method generally uses more complete independent knowledge of the standard distribution. However, its accuracy depends upon the quality of that distribution table and upon correct cumulative integration of the chromatogram. The Hamilec method requires less characterization information, but produces a calibration influenced by the distribution shape and chromatographic broadening of the standard. The Yau method attempts to separate the calibration from that broadening by applying an axial broadening correction. No method can create information that is absent from the standards or overcome unsuitable chromatography. The calibration standard must be chemically and physically stable. Its assigned molecular weight information must be reliable. The chromatographic separation must be governed primarily by size exclusion. The detector must respond appropriately and remain linear. The SEC baseline, processing range, flow rate, and temperature must be controlled. Choosing an SEC calibration strategy. When suitable narrow standards of the same polymer type are available, direct narrow standard calibration is generally the clearest approach. When only standards of a chemically different polymer are available, universal calibration may provide an appropriate conversion if reliable Houwink constants or measured viscosities exist for both the standard and sample materials. The Q-factor method offers a structural correction, but has significant limitations and is now rarely preferred. When narrow standards are unavailable, a characterized broad standard may be used. A complete molecular weight distribution table supports the integral method. Published Mn and Mw values support the Hamilec method. When column broadening can be estimated using column sigma, the Yau method provides a corrected variation of Hamilec calibration. The choice of method should be based on the available independent information and the assumptions that can reasonably be supported. A calibration should not be selected merely because it is the easiest one to configure. The resulting molecular weight values are only as defensible as the standards, physical constants, chromatographic conditions, detector response, and theoretical model behind the calibration. Conclusion. SEC calibration connects chromatographic position with molecular size and molecular weight. For a polydisperse material, there is no single molecular weight. The distribution is described using averages such as Mn, Mw, Mz, Mz plus 1, and Mv. The separation itself responds to effective molecular size rather than molecular weight alone. For this reason, chemically different polymers can produce different molecular weight calibration curves on the same column. Narrow standards of the same polymer provide the most direct calibration when they are available. Universal calibration attempts to remove polymer-specific differences by using molecular length or, more successfully, hydrodynamic volume. Hydrodynamic volume is related to intrinsic viscosity and molecular weight through the Mark-Houwink relationship. When narrow standards are unavailable, broad standards can be used through the integral, Hamilec, or Yau methods. Each approach requires different information and carries different assumptions and limitations. The integral method uses a cumulative molecular weight distribution table. The Hamilec method uses Mn and Mw, but produces a curve influenced by column broadening. The Yau method attempts to correct that influence using the column sigma value. Understanding these distinctions is essential. An SEC calibration curve is not merely a mathematical line fitted through a set of points. It is a physical model connecting elution behavior, molecular size, molecular weight, polymer chemistry, viscosity, and chromatographic broadening. In the next video, we will continue with advanced SEC theory. We will examine how to interpret molecular weight distribution plots, why different distribution traces and molecular weight markers occupy particular positions, how axial correction changes calculated results, and how advanced broad standard calibration information can be derived. Thank you for watching. For more chromatography theory, Chromperfect training, technical articles, and product information, please visit www.chromperfect.com.